So welcome everyone to the seminar on the groups and invariant theory. Our speaker today is Giovanni Cerulli Irelli from the Sapienza University of Rome. And the title of his talk is Symmetric Representation Theory of Quivers and Connections with Li theory. So Giovanni, we're looking forward to your talk. Please begin.
Yes, thank you very much for this invitation. I'm really honored to speak in front of you, and thank you for coming. So this seminar is my attempt, together with Magdalena Bos, who is, maybe will join, she will join later, to understand some algebraic varieties arising in Li theory. So some algebraic varieties, very easy one in Li theory, and how to understand with an action of a group and understand these things using the representation theory of finite dimensional associative algebras. So, and I encountered this connection in my research at least 2 times, even more. So the examples I have in mind are, and I want to discuss today, concern the following. So the first one is the classical case of conjugacy classes. So by me, this means GLN acting on its Lie algebra by conjugation. And the first example that I want to mention is a connection with 2 nilpotent B orbits. Where B is the Borel subgroup of GLM. And then the third thing that I hope to mention are connection with the degenerate, so Evgeny Fagin, degenerate flag varieties. And connection with quiver Grassmannians. So the aim, mine and Lena's aim, so our aim is kind of generalize those known connections to the case where the group, acting is the orthogonal group for the symplectic group. So very humble like case, very humble aim. Okay, and then it turns out that to do so, there is a tool which is algebras with self-duality. Before, but in 2002, Derksen and Byman, I want to mention this. They call it symmetric quivers. Okay. The problem is that the representation theory of algebras with self-duality is not well developed. So there are many things that are still missing. And so we are trying to fix that with Lena. In particular, by more precisely what we want is, of course, description of orbits. and orbit closures. So there are some good news and some bad news that I want to share. But first of all, let me start by recalling. So I assume that you are not familiar with the representation theory of associative algebras. So I will fix notations there and recall some facts. Okay, so that's the first part. Lena's here. Hi, Lena. Yeah. Okay. So representation varieties of algebras. So these are the algebraic varieties arising in the representation theory of finite dimensional algebras. And so I will try to be very concrete. So we start with a graded vector space, finite dimensional vector space, VI. And so VI is a finite dimensional complex vector space. And the set of indices, so the grading is on a finite set that I always fix to be 1 and n. And this finite set is called the finite set of vertices, but it's just a finite set. And the variety is very simple. It's just a vector space, so it's an affine space, is direct sum of homomorphic space between these fixed vector spaces. And here the grading needs then two indices, I and j, and then we encode this grading into some finite set. So Q1 is the finite set of arrows. So it's a finite set, and then every element of these finite sets encodes two vertices. So this is the finite set of arrows.
Do you allow loops?
I allow loops. Yes, why not? Yes, yes. At the moment, it's just what I insist on is that this is just finite direct sum. These are finite direct sum and finite dimensional vector spaces. Okay, and then the group acting here naturally is just a product of GLBI. So this group acts on R by change of basis. So an element of this group is a collection of invertible matrices indexed by the vertices, and an element of R is a collection of linear maps indexed by arrows. And so the action, so if I act with G with if G acts on X, and the alpha component of this action is just Gj X alpha Gi inverse. Okay, so very simple, very natural action to study. And then inside R we can consider some subvariety, affine subvariety. So we allow to consider so affine subvarieties which are closed under the action of G. And these varieties are given by some conditions like, so these are points X alpha such that something like XP is 0, where P is linear combination of composition of arrows. So something like, so say, I don't know, C I1 IK, alpha I1 alpha IK, and then I want that these arrows are compatible. So alpha I1 alpha IK. So these are composable. And then I just require that X is the set of all set of matrices such that when you multiply them following some fixed path, they are 0. So very easy. So these are kind of easy, algebraic affine varieties with a G action. Okay, so these are the varieties arising in the representation theory of algebras. Now let me give you examples which are related to the plan of the talk I mentioned in the first slide. So let's take P. To B is just Cn. So in this case, Q0 is just a single point. And R is end V. And inside R, we take the variety X that I sometimes will use the notation NK. So this is just the set of matrices, n times n matrices, which are k-nilpotent. Okay. So in this case, so Q1, then you see that Q1, to answer the question before, is just one arrow, alpha, that goes from 1 to 1. So then one represents this situation by a loop. Okay. All right, so then the group G is just GLN, and the action on R is conjugation. Okay, so let me record some facts about this action and this interesting variety. Then the G orbits are parameterized by partitions. Of K, so given a partition, say lambda, lambda 1, lambda H, it corresponds to the G orbit of the matrices having, the matrix having Jordan blocks. So here J lambda I is the Jordan block, the nilpotent Jordan block, lambda I times lambda I. Yes. Okay.
Why partition of K? Partition of N?
It's a partition of N. Sorry, yeah, of course. Yes. Yes, so we display them as usual like this. Lambda 1, lambda H. Okay.
So it must be rather partitions of N not exceeding K, or into pieces not exceeding K, or
Yeah, so let me just consider the whole nilpotent variety, okay, just to be sure. It doesn't really matter here. Yes. Okay, and so G orbits are nicely described in a combinatorial way. And what about the generation order? So in Pn there is a dominance order. Which I recall is lambda is bigger or equal than me if sum of lambda I 1 to k, sum of mu I from 1 to k for all k. which is actually equivalent to say that the sum of the columns, something like this. So these are the columns for all K, which is equivalent to rank of, so this matrix, let's call it A lambda, okay? So the ranks of A lambda to the K is, or maybe K minus 1, is bigger or equal than the rank of A mi, K minus 1. So the G orbits are parameterized by just looking at the rank of the powers, and this gives an ordering. And so yes, and then there is the following known fact that, so theorem so this is classical Gerstenhaber Hesselink theorem, which says that A mi is contained in the closure of the orbit of A lambda if and only if lambda is bigger or equal than mi, and G A lambda is equals to G A mi if and only if lambda is equals to mi. Okay. Okay, so now what about the connection with the yes, okay, so this is what I wanted to say about this case. Okay, now just 1 second. Okay, this is known. Okay, let me give you other examples. So another example is take V to be V1, there is some V2, and R to be just one Hom space. And now the group acting is GLV1 times GLV2. Here G orbits are in bijection with the ranks, of course, as we teach to our student. Okay, so in this case, the quiver underlying this variety is just, it has 2 vertices and 1 arrow. Second example, again, V is V1 plus V2, and R is Hom V1 V2 times Hom V2 V1, and inside R we can take X to be the pairs A, B, such that, for example, AB to the n is 0 and BA to the n is 0 for n big enough. Okay, fixed. Okay, so we fix n, and then, so this case is considered by Kraft-Procesi in their famous paper on the description of the Kraft-Procesi. And it corresponds to the quiver having, again, 2 vertices, but 2 arrows, one going from 1 to 2 and the other one from 2 to 1. Okay. So about the representation theory of quivers, let me recall why they are interesting. Because there is the following result. Yes. So theorem. This is due to many people. So it started in the 80s with Abeasis Delfra. By Zvara. And the theorem says the following. Suppose, so I will be a bit informal, but I hope you understand. Suppose that X contains finitely many G orbits. Actually, this must hold for every dimension vector, okay, for every dimension. But let me just say, so there is a finiteness hypothesis on the variety, okay? Then, given 2 points in this variety, Y belongs to the closure of X, of the orbits of X, if and only if. And then you see here in the previous examples, the condition was about ranks. But ranks in the general case can be interpreted as a dimension of a home space. And this holds in full generality by this beautiful theorem of Zvara. So dimension of the homomorphing space. Okay, so X. Z is less or equal dimension of homomorphing space between Y and Z, where Z varies in some set, in the set of indecomposable, in the finite set, indecomposable representations. So in this theory, there is Krull-Schmidt theorem. So every representation is a direct sum of some indecomposable objects. And then suppose that there are only finitely many of such kind of basic objects, these indecomposables. Then looking just at the homomorphing space between X and every such object gives you a criterion for the generation. So it gives a description of the orbit closures.
So when you speak,
yes,
when you speak about indecomposable representations, you mean representations of the quiver with relations.
Exactly. Very good. Yeah, very good remark. Absolutely. Yes, yes, yes. Of the quiver with relation. Yes, yes, yes. So, for example, if the quiver is this and with nilpotence relation, so then the indecomposables are just the Jordan blocks. The nilpotent Jordan blocks. Every nilpotent Jordan block is indecomposable. In the case of this quiver here, the indecomposables are obvious ones. So it's something like C. So it's just so C0 and then 0 C. So these are the points of the variety where the matrices cannot be written in block form, in block diagonal form for every arrow. Okay, so it's something. Okay, and so this description is very useful. So let me recall, for example, one success of this. So for example, this theorem can be used to prove Gerstenhaber Hesselink theorem. On conjugacy classes. As you may know, this proof of Gerstenhaber Hesselink is not completely transparent. It's quite complicated. There are several cases, but using this theorem of Zvara, the proof becomes transparent. It's very easy proof. You find it in a paper of Bongart's. So that's why using representation, if one realizes that some variety is a representation variety, then one hopes to use this theorem to get information about the orbit closures. So let me recall a success of this. So let me recall the construction of Lena with Marcus. So the construction of Bose-Reinecke. Okay, so fix flag. So U1, U2, UN minus 1 inside UN, which is just CN. So I need to give names to the inclusions where UI, so here we fix the standard basis that I call E1 EN, and then UI is the span of the linear span of E1 EI. Let B to be the stabilizer in GLN of the flag. So these are just the set G in GLN such that G of UI is equals to UI. So it's the Borel, the standard Borel subgroup of GLN. Then and let X to be N, so just the nilpotent variety. A. Okay. Okay, then B acts. So the action of G of GLN on X restrict to an action of B on this nilpotent variety. And now consider the following construction. Let's consider the following variety. X is F1, Fn minus 1, and then some A. So the Fi's are just linear homomorphisms between the UIs. And A is in the nilpotent variety. And so the condition is something like, for example, A to the N is 0, or A to the K is 0. Okay. And let's project this into just the sets of Fi's. No conditions, okay? All right, so here in the curly X, there is the action of the structure group of a quiver. So this G, so sorry, there is no space, sorry. So product of GL UI acts on X by change of basis, and G acts here, and the projection map is G equivariant. And now look at the point, a special point here, Y0, which is the collection of this I1, I, N minus 1. And let X to be the fiber over Y0, over the orbit of Y0. And let's project it into Y, not curly, which is just G of Y0. So X is just the variety of some, so Fi and then A, such that Fi is injective. Okay, what is nice here is that the fiber over Y0 is precisely the variety of, so A to the K is 0, okay? The nilpotent variety. Okay, and the stabilizer of the point Y0 for the group G is naturally isomorphic to the Borel group. And here the isomorphism is simply take G here and then sends G to U. There is a general construction that says, well, then X is isomorphic to the associated fiber bundle. Okay, this means, very importantly, that the inclusion of the fiber inside the total space, so the inclusion induces bijections between B orbits in F, which is the object we are interested in. So B orbits in the nilpotent variety and G orbits in X. So this is the object we are interested in. And this is not very interesting in itself, but here we can use Zvara's theorem. So we can use representation theory of algebras to describe G orbits and their closures. So a little problem. If K is bigger than 2, there are infinitely many orbits. So Zvara's theorem does not apply. Okay, so to get the power of this tool here, we need to assume that K is 2, which is already an interesting variety to study. Okay, so then we are left with the following quiver with relation. One, two. So recall that we want to realize this X inside the representation variety. So we need quivers of vertices and arrows, and relation is alpha square is 0. Okay. So, and this has a very nice string algebra. So the representation theory of this algebra is very well known. And so the indecomposables are in bijection with connected walks avoiding the relation. So I'll give you an example. So just to say that there is a kind of classification of indecomposables. There are only finitely many indecomposables. They can be described, and so one can apply Svaras theorem here and get information about the orbit closures. So, for example, so this algebra is very famous because it's the first algebra where there is an example of an indecomposable that degenerates to an indecomposable. So orbit closure contains an indecomposable. So for example, for N2, so the quiver is just this, and the indecomposables are so 1, then 1 can go to 2, 1 goes to 2, and then 1 follow again the path here. Or there is another indecomposable, very interesting, 2, 1. Then 2, 2, 2, 2, 2, 1. So this is alpha. And then actually remark, this algebra is famous because this indecomposable contains in the closure this other indecomposable. Yes. Because when they found it in the 80s, they were thinking that the generations were only given by extensions. So that only, right, but then they found this example. Okay, so so what is the generation order? So it's given by Svaras theorem, described by Svaras theorem. So, for example, for n equals 2, the ordering is the following. So this degenerates to this, degenerates to the 0 matrix, or for n equals 3. Oh, sorry, I didn't tell you what is this. sorry. Yeah, I didn't tell you about the oriented link patterns. All right. Okay, then using this, Bose and Reinecke, they say, okay, then, yeah, I didn't say here the fact that this preserves orbit closures. So this is again the fact that there is such a associative fiber bundle. So there is this general construction that allows to study B orbits inside the representation variety of a quiver. And then also, and the orbit closures for the Borel, they correspond to orbit closures for the structure group of the quiver. And the orbit closure for the structure group of the quiver are described by Svaras theorem. And actually, what Bose and Reinecke, they say the following. So then B orbits in N2, they are in one-to-one correspondence with what they call oriented link patterns. So I illustrate this just, so for example, for n equals 3, now for n equals 4, let's take this oriented, so 1, 2, 3, 4. Then this combinatorial object corresponds to the orbit of the matrix, where so 2 go, so 3, 1 goes to 0, 2 goes to 4, and 3 goes to 1, and 4 goes to 0. Okay. And so this is the parametrization of the orbits, which, so parameterizing B orbits with this combinatorial gadget is actually very nice, I think. But they also, using Svara's theorem, they can describe the generation order. So actually, let X be an oriented link pattern on n vertices, and AX the corresponding matrix. Yes. So, and then define for every k, 1 to n, the following two numbers. So pkx, so that's the number of vertices which are so such that which are smaller or equals than k, then vertex k, not incidents with an arrow, plus number of arrows of the link pattern of X, whose target is on the left of K. Okay, something like this. So something that you can, is a number attached to the link pattern. The link pattern is just collection of some arrows. And then there is a combinatorial object, and then you attach to this combinatorial object such number for every vertex, and this other number. So this is pkx plus something. So it's just okay, just to give you a flavor of what kind of invariants they found, and they come directly from Svara's theorem. Okay, and then the theorem is that the orbit of AX, so this is Bose-Reinecke, contains some the orbits of another matrix corresponding to a link pattern Y, if and only if these numbers pky and then qk. Now this depends also on L. X QKL of Y for every K, then for every K and L. Okay, so this kind of description of the orbit closures is what we would like to have for the orthogonality symplectic case. So this is the question that I and Lena asked to ourselves. And then we ended up with the following. So suppose now that yes, yes. So symmetric representation varieties. So we have to modify the definition of the representation varieties. So and then let us be inspired by the classical case of conjugacy classes. Then in that case there is a matrix in the Lie algebra of the orthogonal of the symplectic group, which means that this matrix is symmetric or anti-symmetric with respect to a bilinear form. Let's say anti-symmetric with respect to an epsilon form. So, but now we have a graded vector space, Vi. So, and then we need to endowed this with a bilinear form with a non-degenerate bilinear form. And we want, so in this theory, well, we want to identify a vertex, so a vector space in a vertex with the dual vector spaces in another vertex. So this form is not too complicated. So we want that the form restricted to Vi times Vj is 0. Unless J is some fixed vertex, so that that depends on I, so we call it sigma I. So then we want that sigma is an involution. So this means that V sigma I is identified with the dual vector space of Vi by the form. Okay. All right. So, and now we also want that this form is symplectic or orthogonal. So fix epsilon equals 1 or epsilon equals -1, and then require second condition. So require that VW is equals to epsilon WV. Okay. Then this form is called an epsilon form on the graded vector space V, and this form is compatible with sigma. We say it's compatible with sigma. Okay. And now that we have this quadratic space V with this non-degenerate form, we can consider the group of isometries. Let G V form be the group of isometry G such that so this is what this is very simple. It's just product of GLVI for I different than sigma I times some product on the vertices which are fixed by sigma on Vi, and then the restriction of the form on Vi. And this group is just orthogonal if epsilon is 1, or symplectic if epsilon is -1. Okay. So, all right. And then, so we have group, and then we need a variety to act on. Of course, there is the variety of, recall R to be the representation variety. But we want to consider subvariety. We want to consider anti-self-adjoint points of R. So we want something that lies in the Lie algebra of this group, of this isotropy group. Okay, so what do we want then? Then you see we have to require something about the arrows, because here there is no request on the arrow. So sigma is just some bijection between the vertices. But so, and then what do we want? So recall that if V and W are some quadratic space, then the adjoint goes on the other side, right? And is defined by, so here there is some form, here another form. So let's say 1 and 2. So then the adjoint is defined by saying that FVW2 is equals to VF adjoint W1. Okay. So then this means that if there is an arrow from I to J, then we want that the adjoint goes from sigma J to sigma I. So so what we want is that for every arrow ij, there exists an arrow, let's call it sigma alpha, from sigma j to sigma I. So sigma must induce orientation reversing bijection on the arrows. Okay. Good. Okay, so fix this. Suppose that there is such a thing. Then inside R, we take R epsilon to be just the variety F alpha in Q1, such that the corresponding sigma alpha is minus the adjoint of F alpha for every alpha. Okay, so that's the natural generalization of the usual condition. So this means that this F lies in the Lie algebra of the isotropy group. Okay, now 5 minutes are left to present the main results here. Okay, and then what's the situation? So we have R acted upon G, and inside there is R epsilon, and this R epsilon is acted upon G V. So the isotropy group, let's call it G epsilon, for which is a subgroup here. And then the following, the first theorem is well known. There is a paper of Magyar, Weimann, Zelewinsky. But I and Lena give another proof of the theorem in this case. So the theorem of Magyar, Weimann, Zelewinsky is more general, but in this case of representation varieties of algebras, we give another proof, which is homological. And there is also another proof in some special case by Derksen and Weimann. And it says the following, okay. So, and here there is also X and X epsilon. So we allow also relations, okay? So the theorem says that for every X in X epsilon, then the orbit of X by the B group intersection with the variety of this anti-self adjoint points is precisely the orbit by the small group. So for example, this theorem is saying that if two symmetric matrices say n times n matrix are congruent if and only if they have the same rank. All right, and so this kind of solves somehow the first question about description of the orbits. Okay, but then the much more difficult question concerns the orbit closures. And then the theorem 2 by myself and Lena says that it's not true that so this is not true in general. And so we have a counterexample that I want to mention, because this counterexample comes from our study of B orbits. So it was inspired by the following. Okay, so take the following matrix. So this is a 2L times 2L matrix. So this is L, 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 1, minus 1, and N to be the matrix having 1 here and 1 here. So then M and N, these are two nilpotent elements in the Lie algebra of the group of type D. So orthogonal group of 2n. Then N belongs to the orbit closure of B, where B is the Borel group of GL2N, but the dimension of B epsilon n is equals to the dimension of B epsilon m, where B epsilon is the Borel subgroup of the orthogonal group. Okay, so this where our counterexample comes from. And now in the last 2 minutes, I want to give you a positive answer to the orbit closures, which is
Giovanni, actually you have half an hour.
Really?
Yes.
Ah, I thought it was 1 hour. Okay.
No, I wrote it. It's 90 minutes.
Okay.
Of course, you may finish earlier, but feel free to tell us everything you want in this half an hour.
Okay, perfect. Okay, thank you. Sure. All right. So this counterexample, well, was found by myself and Lena, and then we showed it to Paolo Papi, and then he said, of course, it's a counterexample. But well, it was not easy to guess. So because one would like to, since we have a nice description of the orbit closure for the Borel subgroup of GL, it would be nice to have the same ordering induced on the Borel, on the action of the Borel of the orthogonal group on the nilpotent matrices. But this is not the case. Actually, we conjecture that in type C is true. So the generation of the order for Borel action of GLN induces a degeneration order for the Borel action of the symplectic group. Okay, and now the last theorem is, this is actually for me, it was very, very hard, but it's now done. So, and it can be formulated as follows for symmetric quivers. Of finite type. The generation order.
Excuse me?
Yes?
May I ask you the question about the previous thing?
Oh, yeah,
Told,
sorry.
Yes. You told that in symplectic case, this is defined by GLN. And
conjecture.
I know that
this is conjecture.
No, I know that this is true.
Really?
If we do not look, if we do not look on all the orbit, but only on the part of intersection with upper triangular matrices, then it is true. My student showed it. And moreover, in orthogonal case, this is true in 2n+1 for B. It is also true. It is not true for D. It is not true.
I see.
And there are, first of all, there is one reason that E1 plus E2 and E1 minus E2 are of the same one. One of them is in the closure or in GLN, but not in D.
Yeah, so this is precisely this example. Yes, yes. Thank you, Anna.
So I wonder if it is, and again, I never worked with all the orbit. I always worked only with the intersection with upper triangular part. But in the upper triangular part, both of these results are very natural and simple. It does not work only in D.
I see.
In D, we could not find, we conjectured what is the closure in this case, but we do not have the proof.
Thank you, Anna. That's okay. Okay. So in the upper part is true for type C.
Yes.
Nice. Okay.
Yes.
Nice.
And for B and C it is true.
Okay. True for B and C in the upper part. Nice. Yes, thank you very much. Yes. And in type D, do you believe it's just in the irreducible components of the varieties induced? Because
I don't know.
In type D, there are two irreducible components, and maybe if one restricts there, the order is induced. We don't know, but okay.
No, it is more gentle. It is more. We had a conjecture, but we could not prove it.
I see. Thank you very much. Okay, nice. Thanks. Okay. So yes, so this the last theorem concerns more the connection with degenerate flag varieties, and so this is somehow, yeah. So it says for symmetric quivers of finite type, the degeneration order is induced, and so by finite type, I mean the following: we take Q0 to be 1n, and then we fix a sigma naturally, and then assume that Q0 is ordered form a poset. Such that if I is less than j, then sigma j is less than sigma I. And then in this case, put an arrow. Let's say ij, if there is a cover. So ij is a cover. Okay. For example, the situation here is something like 1, 2. So the equivalented case. This is one very interesting case. Another one is, for example, this one, 1, 2, 3, which is sigma 2, and then 4, which is sigma 1. And then another example is this one, 1, 2, 3, 4, which is sigma 2, and 3 is fixed. And then 5. Okay, then in this case, it's true that the generation order is induced. So for this kind of varieties here. And our proof uses Auslander-Reiten theory. But hardcore, I mean, I'm not still satisfied with the proof. It was really, really hard. Okay, so this is what I wanted to tell you. Sorry to bother you. I try to be a bit like, well, okay, so I finish here. Thank you for your attention.
Yeah,
Yes.
Thank you very much. Great talk. So
Yeah.
do we have other questions or comments, suggestions from the participants?
Yes.
So coming back to this first general theorem of you and Magdalena,
Yes.
so there is, am I right that, so do I understand right that there is no assumption on the representation variety? No relation, I mean,
No.
the relations are unrelated with this symmetric structure, just any relations.
Exactly. Yes.
Okay.
Yes. Yes. Actually, the proof of Magyar by Mazzelewski uses some number theory argument. It's not difficult. It's actually they didn't even, yeah, it's not difficult. And our proof uses some, well, group actions, but yeah, it's not a difficult theorem, but it's very surprising. So, and probably it's well known. And maybe it holds in more generality when there is not only an involution, but something like with to some power n is the identity, sigma to power n is the identity. Maybe it holds in that case as well. But for the orbit closures, it's wrong. And as Anna knows very well. Yeah, we didn't know, but
thank you.
Yes.
Giovanni, about this Magyar-Mazzelewski theorem, was it the same paper where they were dealing with symplectic flags, or?
Exactly. Yes. Yes. They wanted to describe symplectic flags, and so they reduce it to the case of GLN flags for simplifies a bit. Yes.
And I wonder that, well, you see that in their case, CN was behaving like way better than DN, because I think they didn't manage to do the DN case. And I wonder if it is related to the fact that you and Anna explained that something works in type C, and well, we hope it works in type C, but it doesn't work in type D, certainly.
That's a very interesting remark. Yeah, it could be. And Jerzy told me that the D case was done recently by a guy from Japan, I think.
Yes,
I don't remember.
You don't want to read this proof.
Yes, maybe it's the same problem. Yeah, the orbit closures is complicated. But yeah, I wonder if what kind of conditions one can put on X and G in order to have the orbit closures. Maybe irreducibility could be one, but maybe Anna knows better. So.
Am I right to remember that all two-step nilpotent orbits are spherical? So this finiteness result stems from the general results of
absolutely. Yes, yes. Actually, there is a description of the orbit closures by Papi, Moseneder, Gandini, and but their description is it's quite hard to apply in explicit. If one gives explicit matrices X and Y, it's hard to understand if one is in the border of the other, because they uses the order of the Weyl group for the affine quiver, and so it's complicated. Even this example here with their technique was not complete. For example, this was not completely trivial to work out.
By the way, this example can be reformulated for the symplectic case. I guess you tried it.
Yeah, for the symplectic case, it works perfectly.
So,
yes.
So there is no counterexample.
No. Yes, yes, because as Anna said, so these matrices are lower triangular, but there is a similar result with the transpose matrices. So also in the upper part, there is the same phenomenon as Anna was saying. So this is related to the outer automorphism of the orthogonal group or even orthogonal group. Yes, the outer automorphism gives an automorphism, gives an isomorphism between the b orbit of n and the b orbit of m. So these two, they don't only have the same dimension, they're really isomorphic as varieties by the outer automorphism of the linking diagram. Okay.
No, well, may I ask? I would like to recall that a reductive group is sometimes exists of exceptional type. And what about quivers theory, such that orbit is some exceptional group orbits? Maybe some people make something in this direction. Is a question.
Yes, that's an excellent question. The fact is that the representation varieties for quivers, they are always of type A. The group is always a product of GL. So the first attempt was by this Dersen and Weimann, where they include this symplectic and orthogonal case. So where the group we could get is this, where is it? Yes, here. So product of some GL and then some orthogonal group or symplectic group. And then one can mix them. This is also easy to do, but no, I've never seen exceptional groups acting on representation varieties associated to quivers. But that's an excellent point. Yeah, I don't know.
Well, thank you.
Sure, thank you.
Right. Anyone else wants to ask something? No? Well, maybe I do. How do you get in the symmetric case to the B orbits? It somehow escaped my attention.
Yes, excellent question. Yes. So yeah. So I want to mention this. Thank you. So in that case, the algebra must be modified as follows. So L, then omega, then some kind of L star, 1 star, and then A, B, and the relations are alpha square, and then BA. So the reason here is that the flag is, so we have this flag, UL, and I don't know, for example, C2N, and then it projects into yes, so we want this to be isotropic, so here we have to take yes, UL orthogonal UL, yes, yeah, something like this. So this is isotropic, yes, isotropic. So the quiver must be this one. So this was really clear to me already many years ago. So we have a candidate to describe to have the Bose-Reinecke description of B orbits for type C, B, and D. And we know how to describe, so there are symplectic and orthogonal link patterns, oriented link patterns, but we don't know how to describe the degeneration order. It's much harder. I mean, from the quiver side, because already for type A quivers, this theorem here is really complicated. I mean, at least the proof is not easy. And so try to do it in this, for this algebra.
You have a loop.
It's not because of the loop, it's just because, I don't know, it's complicated. Yeah, the representation theory of this algebra is easy. It's just a string algebra of finite type. One can describe the indecomposables, etc. But we don't know how to describe the symmetric degeneration order. Because if it's not induced, then what else remains? So, yeah.
Yeah, well, it's more complicated. But if without a loop, you will have a finite type or not? If you remove the loop alpha. it's
yeah.
finite.
If you remove the loop, it's finite type. But also with the loop squared 0, it's already finite type. It's still finite type. So this is finite, very nice algebra. So it's just
Your relation is alpha squared is equal to 0.
yeah, alpha squared is 0, and also the composition of these two arrows is 0. This is the algebra. And yes. So right.
Thank you very much. I think we had
Sure.
nice
Thanks
discussion.
a lot for the invitation. Thanks for your remarks. Thanks for coming to my talk. Thank you very much.